Depth charge here for another math tutorial video, and today we're going to do some trigonometry, specifically in the introduction to how the unit circle is analyzed, but this video is introductory to that, and so we're not actually going to be looking at the unit circle. We're going to be looking at the fundamental concepts behind the unit circle, so let's get to it. Here's the scenario. We want to find the 6 trig ratios. And what's going to be given in these problems in this video is a point in each case. And what we have to do is draw a rotation that goes with that point. And then we can draw a triangle, and then from there we can get the 6 trig ratios. The way this is worded can be rather tricky to see what all the words mean, all the terms mean, but what this simply is talking about, so we want trig ratios given the following points on the terminal side of the angle in standard position. We're going to draw a picture that illustrates that, so hopefully it should become clear with the drawings. That is simply saying we have a point in a quadrant. Typically there are 4 quadrants, we'll get to that, and that point implies a rotation from start to finish, and that start is going to be what we call the initial side, and the end is going to be the terminal side. So where is 3, 4? 3, 4 is going to be illustrated right about there. And what we're going to do is we're going to draw a line through 3, 4. And draw a rotation, just like that. Now, the 6 trig ratios is what we need from this. This is quadrant number 1. And then there is 2, and there is 3, and there is 4. What you have here is a scenario where you start at the initial side and end at the terminal side. Beginning, end. We don't know this angle, nor will we determine this angle in this video. What we do have is the ability to draw a triangle. And this is going to have a length of 3, and this is going to have a length of 4. This length is unknown, which we're going to call r. Not the hypotenuse of a triangle in geometry terms, even though it is the hypotenuse of a triangle in this case. R actually stands for radius. And well, like I said, we'll get to that in a future video when it comes to the unit circle. So it is the hypotenuse of this drawing triangle, but we don't want to think in terms of triangles per se when it comes to the 6 trig ratios given that point, because these are technically not lengths, these are actually coordinates. Now they correspond to lengths, and I can redraw this triangle if I need to. Let's do that. Draw it a little bit bigger. Three, 4, R. And this should be obvious what R is, because x squared plus y squared equals r squared. The x appears to be a length, but it's actually a coordinate. The y appears to be a length, but it's actually a coordinate. 3 squared plus 4 squared is going to equal r squared. This is 9 plus 16. This sum right here gets us to 25. We square root both sides, and we get that 5 equals r. That is a very important calculation because it allows us to get the 6 trig ratios. You can't get the 6 trig ratios without r. Another way to think of r is given a point, and like I said, here are the instructions. We have a point and we want the 6 trig ratios. And the ratios are achieved by performing the ratios of 3 different numbers 6 different ways. We have 2 of the numbers, we need the third, which we got. There are 6 trig ratios and there are 6 definitions of those ratios. And in geometry we learned SOHCAHTOA, which can help us, but we are not going to use SOHCAHTOA per se. We are going to use another definition that is related to this. The angle could be thought of as being right there in this case. That's another thing to be very careful with in the future. It works here, where the angle of rotation is the angle in a geometry sense, but it doesn't always work that way. It does in this case. Sine of the angle is going to be opposite over hypotenuse, which is 4 over r. Cosine of the angle is going to be adjacent over hypotenuse, which is 3 over r. And tangent is going to be opposite over adjacent, which is 4 over 3. But like I said, we're not in geometry. This is a pre-calculus and a calculus topic. The definition of sine that we're going to use instead, sine of the angle, is going to be y over r. Not opposite over hypotenuse. Y over r is going to be 4/5. This is the sine ratio, 4/5. There are 6, and we've done 1, so we've got 5 to go. Cosine of the angle, here it's adjacent over hypotenuse, but we're actually going to see it as x over r, where x is a coordinate, not a length, and r actually is a length. And this is going to be 3/5. Tangent of the angle is not opposite over adjacent. It's actually going to be the y coordinate over the x coordinate. Which is 4/3. That's half of the 6 trig ratios. The other half are simply the reciprocals of these. The reciprocal of sine we call cosecant, which is r over y. R is the length from the point to origin, and y is the y coordinate, which is given. Secant of the angle is going to be the reciprocal of cosine, which is r over x. R we calculated to be 5, and x was given to be 3. And yes, you can skip this step if you know that secant is the reciprocal of cosine, which it is. We're not going to skip steps as far as writing down equations in this video. cotangent is a reciprocal of tangent, which is x over y, which is 3/4. So, a lot of information in a small space. Given a point, we have a distance from the point to origin, which is 5 in this case, and from there we make 6 ratios, and there are 6 equations for that, which need to be memorized at some point in these math courses. Alright, so that was in the first quadrant. Let's go to the second quadrant and do the same thing. Again, the instructions are as follows. Given a point, imagine that point represents a rotation, and find 6 trig ratios. This is going to be in the second quadrant. So that could be a representation of -512. Now, here's where we see the difference between geometry and trigonometry. We call this the initial side, and we call this the terminal side, meaning there's a rotation implied with this point, and it is not acute. We don't know it. We could find it, but we're not going to. We know it's obtuse, and it's in between 0 and 180. If we were to draw a triangle, and it's very tricky to draw triangles when you have rotations that result in quadrants other than the first quadrant. This is quadrant 2. You can think of a triangle. This is a right triangle, absolutely. This length is 5. This length is 12. And you can draw a triangle if you so desire. Five, 12, R. This is R right here, the distance from the point to origin. These are appearing to be exactly the same thing, and they are in the triangle sense. This angle right here that my pencil's pointing at is not theta. And I've seen other videos that do a good job in explaining this, but what I've unfortunately seen in these videos is that they look at this angle right here when they're doing these ratios, and that is not what we do. We look at the angle of rotation to get the 6 trig ratios and the coordinates and the distance from the point to origin. What is R? This is Pythagorean theorem, but these are coordinates, not distances. That's a very important distinction. We're not going to use 5, we're going to use -5. Yes, we're squaring it, but it's very important to distinguish what we're talking about here. The y is going to be 12, and there it is. These parentheses are very important. (25), 144 added together give us 169, which equals r squared. That is a perfect square root. This problem was designed to give nice clean numbers in our answers. Square root both sides. 13 equals r. Well, that's great. There's r. There are 6 trig ratios, and there are 1, 2, 3 numbers. And with 3 numbers, you can make 6 ratios. Let's do it. Writing down all the equations. Sine of the angle. Which angle are we talking about? Not this angle, which is also this angle. It's the angle of rotation. It's going to be y over r, which is 12/13. Cosine of the angle is going to be x over r. Be very careful, it's negative. And that is, again, where we see the distinction between geometry and trigonometry. This cosine ratio is negative. If we were to do the cosine ratio using this triangle, and if we were in geometry, it would be fine to do that. We get a positive ratio, but we actually get a negative ratio with this cosine. Tangent is going to be y over x, which is 12 over -5. If you want to rewrite it, put the negative somewhere else, that's fine. We have very limited room here. 3 down, 3 to go. The reciprocal of sine we call cosecant, CSC, which is r over y, which is 13 over 12. The reciprocal, right there. 2 more to go. I'm going to write small. Secant is going to be r over x. Reciprocal of cosine is secant, which is 13 over -5. And finally, cotangent. It's going to be x over y, which is going to be -5 over 12. There's a number of convenient things in this problem, and that is it's a very common triangle that we used to analyze it. We didn't actually use this triangle in the calculations. We used the coordinates instead of the lengths. R is a length, and that was achieved very easily, I think, with Pythagorean theorem, and it was nice and clean integers. No reduction of fractions needed. If these fractions are not reduced, if they're not simplified, they must be simplified. It's very important. So again, given a point, what are the 6 trig ratios? That's literally the problem. But a third number is needed to get 6 ratios. Next point. Same problem, different point. This point is going to be a different quadrant. This can represent -1, -1. Be very careful with these pictures. This is initial side, and this is terminal side. The rotation is very large compared to what we've seen before. Call it theta. We don't know it, nor are we going to find it. We are, however, can visualize a triangle right there. This r is the distance from the point, -1, -1, to origin. So if we want to, we can redraw the triangle, that's fine. This triangle right here is right here. The distance is 1, 1, and r, and that's fine, but we're not going to use this triangle in calculating the 6 trig ratios. We are, however, going to do x squared plus y squared equals r squared. X and y are coordinates. This is quadrant 3. Notice I'm inserting the coordinates and not the lengths. Yes, you get the same thing, but it is very important to acknowledge that in trigonometry, for sine, cosine, tangent ratios, secant, cosecant, cotangent ratios, we're making ratios using the coordinates of the point of interest, not the lengths of the legs of the triangle, if we were to make a triangle. This is 1 plus 1 equals r squared. 2 equals r squared. We square root both sides. Just like that. And since it's a length, r is a length, we get r to be the square root of 2, which we're going to leave as the square root of 2 and not put in the calculator and get a decimal. Ideally, we do all of these without a calculator. We have 3 things. We're going to make 6 ratios. The sine ratio is defined to be, in trigonometry, y coordinate over r, the distance from the point of interest to origin, which is -1 over root 2. This would be a fine enough answer if we were in calculus, but let's assume we're in pre-calculus. That is an unacceptable answer. We have to fix it by doing what's called rationalizing the denominator. And what you do is you multiply the answer, and this is the answer, but it's not simplified. Multiply the answer by the equivalent of 1. And I'm choosing root 2 over root 2, which is 1, because when you multiply this, let's actually use a calculator to confirm this. I chose to take my answer, multiply it by 1, and I didn't choose a million over a million. I chose root 2 over root 2 because the bottom here is square root 2 times square root 2, which is 2. That is called rationalizing, or getting rid of a square root in this case. So this gets me negative root 2 over 2. This 1 is times root 2, which is just root 2. That is the exact value of the sine ratio. Well, great. 1 down, 5 to go. Cosine of the angle is defined as the x-coordinate over r, which is the same thing. This is a coincidence. Sine and cosine don't always output, and yes, this is an output. Input the angle, output a ratio. But in this case, we do get the same output for sine and cosine. Unacceptable to have a square root on the bottom, so we multiply it by the equivalent of 1, and we get negative root 2 over 2. So we are getting negative outputs for our ratios, which is fine. Tangent. Tangent, as we're going to see, is actually one of the easier ones to deal with because it's just, don't even need r. It is the y-coordinate over the x-coordinate, which is -1 over -1, which does reduce to +1. Very simple. Simplification of the ratio. 3 more to go. Now, like I said before, cosecant is a reciprocal. What are we going to reciprocate? Well, I recommend we actually write down the equation of what cosecant is defined as. And that is the r value, which is root 2, over the y-coordinate, which is root 2 over negative 1, which can be simplified into negative square root 2. One's unnecessary. This is negative root 2. Secant is next, which is the r, distance from the point to origin, and the x-coordinate. R distance is root 2. X-coordinate is negative 1. And there it is. It's the same ratio as it should be in this case. Lastly, cotangent. Reciprocal of tangent, which is x over y, negative 1, or negative 1, and it's the same as tangent. So the tricky thing about this point is, one, it's in the third quadrant. The ratios achieved involve a square root. The r value must be calculated when it's not just provided. So, point, 6 ratios, last one. Since we were in the first 3 quadrants, we're now going to be in the 4th quadrant to end this. Quadrant number 4 to end this. There's my xy axes. That is a reasonable place to put this point. Now, standard rotations. That was actually in the instructions. Let's look at the instructions one more time. Standard rotations involve rotating a particular way, which is counterclockwise. That is a standard, which we call the positive direction sometimes, just like that. That is a big, big angle. If we don't know it, we know it's 0, 90, 180, 270, 360. If you want to, you can label these axes. This is 270, this is 180, this is 90, this is 0, and this is 360. There's my triangle, which I can get the lengths of the legs of the triangle very easily. That is the coordinate, 2, negative 3. R is my distance. The triangle of interest looks like this. There's 2, there's 3, and the unknown R. It will soon be known. Great. There's my Pythagorean theorem equivalent in trigonometry. Once again, these parentheses are vital to making sure we type things in the calculator correctly if we choose to use a calculator. Let me show you the difference here. If I choose to do 2 plus negative 3 squared, gets me that, negative 7. This sum appears to be negative 7. It's actually not. That was a joke. Sorry about that. 2 squared plus negative 3 squared. Much better. That's still wrong. Because in reality, just like that, that is what we're doing. That is 13. Positive 13. R will always be positive. Square root both sides. So R is going to be root 13. 13 is a prime number. This is a topic for certainly another video, where you have to ask yourself, can this be simplified? It's a prime number. There's no perfect square roots that can divide into 13, so it is simplified. All right, we have three things. We have, this is X, this is Y, and this is R. Make 6 ratios. That is literally the problem. The sine ratio. The angle is this rotation angle, whatever it is. Sine ratio is Y over R, which is -3 over root 13. This is not a simplified ratio. It appears to be at its surface, but it's not. What you do is you multiply this ratio by the equivalent of 1. And there it is. So this is the simplified best answer. Doesn't appear to be simplified, but it is. There's no square root on the bottom. It's called rationalizing the denominator. When you get this ratio right here, you change it by multiplying by 1, and it becomes the ratio, the answer. Cosine. There's the cosine ratio, x coordinate over r, which is 2 over the square root of 13. Multiply by the equivalent of 1. Root 13 on top, and on the bottom it's just 13. When you're looking to see if things simplify, things to look for: can you simplify the thing that's square rooted? You can. And this ratio here, 2/13, can that be simplified? It can't. So the cosine ratio is done. Tangent ratio is simply the y coordinate over the x coordinate, which is -3/2. Done. The cosecant ratio is going to be the r distance over the y coordinate, which is root 13 over the y coordinate. And that's it. If you want to place the negative at another spot, that's fine, but we're not going to. Two more. The secant ratio is going to be the r distance over the x coordinate. It's easy to mix up x and y. But secant is the reciprocal of cosine. Cosine involves x. Secant involves x. Our distance is root 13. The x-coordinate is 2. And that's it. Simplified. Good to go. Cotangent of the angle is going to be the x-coordinate over the y-coordinate, which is 2 over -3, -2/3. Simplified, good to go, and that is the sixth and final trig ratio given this point on the xy axis. Hope you found this video helpful. Please hit that thumbs up button and consider subscribing, and please visit my other channels and consider subscribing there. Links are in the description. Depth charge out.